Hi everyone, in the previous classes we have seen the concept of indexing, right? So specifically we have seen single level indexing, right? So single level indexing means we are going to have one level of indexing, right? Basically indexing is meant for to improve the read performance, to improve the read or accessing of data item performance. We are going to go for indexing, right? In single level indexing we have seen primary indexing, cluster indexing and second indexing, along with various kind of problems also we have seen, right? Yes, right. In another kind of classification of indexing we call it as multi-level indexing. Now in today's class we'll try to see the complete concept of multi-level indexing, right? Guys, multi-level indexing means if you are going to have more than one level of indexes, then we can call it as multi-level indexing. I mean, if you are going to have a hard disk, this hard disk is going to be split in the form of block by block, and we have created one index. And this index contains two blocks. Assume two blocks, and this is what single level indexing, right? Coming to multi-level indexing, we are again going to make index once again. Right? If you want to index once again, we can go for indexing. This concept we call it as a multi-level indexing. If you are going to have more than one level, we can call it as a multi-level indexing, right? So why we are going for splitting the index file into again one more level of indexing? Because sometimes your index file itself is not going to fit into one particular block, right? So meaning that if your index file itself you are thinking that is too big, then I may divide or I may create one more index file for it, right? Yes. See, basically if you are going to clearly observe, this kind of indexing will look like this kind of structure, right? So if you try to observe this one in the reverse order, right? Guys, try to observe. It look like something in different manner what you have known earlier one. It's a kind of tree. Right? Yes. So based on that, I can say multi-level indexing contains various levels of indexes, and those levels are available in the form of trees, right? And it can have a root node, it can have intermediate nodes, and it can have leaf nodes as well. Okay, fine. So before going for further, right, I mean the multi-level indexing you can able to implement with the help of ISAM, BTrees and b+trees, guys, right? So let us discuss that one by one in the later part. So before that we'll try to create one kind of a binary tree, right? So what is the meaning of a binary tree? Binary tree means we are going to have two children, right? For example, it is 1, 2, 3, 4, 5, 6 and 7. Simply I can call this as a binary tree. But coming to the implementation aspect, how we are going to implement this one? We will implement in the form of nodes, right? Yes. 1, 2, 3, 4, 5, 6 and 7. Guys, you know this concept, right? It is available, it is stored in the form of nodes, right? So if it wants to connect to this one, you require to have some address here, you require to have some address to connect like this. So this is what we call it as a binary tree implementation, right? Yes. So on the leaf nodes it is going to have the value as null because there are no further children, right? Simply we can say that if you try to take one particular node, this node is going to have value and a left pointer along with the right pointer, right? Now in binary tree, you cannot able to perform search operation efficiently because you don't know where your data might be, right? So for that reason, we'll try to go for some kind of a tree called binary search tree. Binary search tree. So for example, if I are going to assume some kind of a binary search tree like this, it will be something like 4 and a 3, 6. For example, it might be less than, right? Yes, 1. And if I try to take this is 2, this will be 3, this will be 5, and this will be the 7. Right? What is the meaning of binary search tree? Binary search tree is also kind of a binary tree. If you take a particular node, the nodes which are present on the left side should be less than or equal to the node, and the nodes which are present on the right side should be greater than or equal to the node, right? That is what we are trying to perform here. Here it is left pointer, right pointer, left pointer, right pointer, left pointer, right pointer, and all are going to be here null values. This is what your implementation is going to be happen, right? If you are going to clearly observe, if I take a node 4, whatever things that are available on the left side are going to be less than the value 4. Whatever things that are going to be present on the right side that are going to be greater than the value 4, right? This particular property has to be satisfied at every level, not only at the single level. Yes, right. Now in this particular scenario, what is going to be happen? Can I able to apply some kind of binary search algorithm? Yes, right. If I am going to apply binary search algorithm, it is going to take the time complexity of log n to the base 2. Okay, fine. It is good now. But if as my n value is going to be increased, search time is also going to be increased. Am I right or not? Yes. Search time is also going to be increased, so that efficiency of the retrieving the data is going to be decreased, right? So is there any chance to decrease the accessing time even my n value is going to be increased, right? For that, the solution is can we reduce the number of levels here, right? Log n base 2 means what? Simply the number of levels are there here, right? So if I am going to reduce the number of levels in the binary search tree, definitely it is going to reduce time complexity, right? So if you would like to reduce the number of levels, what we can do? Can I increase the data? On the each and every node? Yes, that's better, right? For example, if you try to see, I am going to write down the node structure will be like this: 3, 6, and 1, 2, something like 4, 5, and 7. Right? If you are able to clearly observe here, I have reduced the number of levels or not? Yes. Here I have, in binary search tree, I have the levels are 3. Here I have the total number of levels are only 2, because I have increased the number of values in a particular node. Right? So this is where you can reduce the search time, and you can reduce the number of levels also, right? So this particular thing I can call it as a kind of a BTree, right? So as I am trying to increase the number of nodes, the order of the node is changing, right? In binary search tree, order of node is 2, right? In BTree, according to the order of a node, we can change its order. We can change the degree of the node, right? So in this particular scenario, the order of the node is 3. In this particular scenario, order of the node is 3. So order means what? Maximum number of children I can able to place in a particular node. Right? If I are able to clearly observe here, the maximum number of children are 3. I am trying to write in the red color. This one will be 1, 2, and 3. Okay, fine. Guys, clearly observe. If I try to restructure the same thing, mm, if I take a particular node, this node is going to have, as per the earlier example 3 6, right, it is going to have left pointer and right pointer and this one, right. This is a kind of thing, it will be connected like this. It is also kind of thing, it will be connected like this. It will be connected like this, right. Yes. So if you are able to observe, this is a kind of a pointer, this is a pointer, this is a pointer. So actually it is going to have 3 childs, and again they are going to be works again different ways, right. Yes. So how actually they are going to be stored, right. So if I say this is one particular like node, this node is going to be another node, 2 nodes, not only exactly like this, it will follow this kind of structure. This kind of structure, if you are able to clearly observe this one. So this is what we call it as multi-level indexing, right, where your data is going to be placed, your whole data is actually going to be available in the data file, but if we are trying to think about b-trees, your data is going to be distributed in all the locations, in all the levels, right. Yes. So your data is going to be supposed to have, will be available in all the locations, not only in one particular level, not only in the lower level, it is going to be available in all the levels, right. So if you are able to observe the complete the structure of a particular node, this is what we call it as a block pointer. If I try to convert in terms of DBMS point, if I would like to connect it to this particular thing, I need a kind of block pointer. This is what we call it as a key. Right. And this is again a block pointer, this is again a key, this is a block pointer, right. So I can call this as block pointer, or I can call it as a node pointer, guys. Block pointer or a node pointer, which is pointing to a block, and this one will be a key. And for every key, as per my explanation, there exists a data. The data is going to be distributed everywhere, right. So for every key, your data is going to be available in which location? In the records, right. For every key there exists a record pointer also. This is important. For every key there exists a record pointer also. So with respect to this one, if I try to say the structure of the node, contains block pointer 1, followed by, for this block pointer adjacent, you are going to have key 1, and you are going to have record pointer 1. After this, you are going to have the next block pointer P2 and K2 and record pointer 2, and so on. And at the end, you are going to have key n-1 and record pointer n-1, and finally you are going to have block pointer n. Guys, right. If you want, you can have the clarity, right. So you are going to have 2 keys, and you are going to have 3 children, right. So how many block pointers are here? Block pointers are 3, keys are 2, and for every key there exists a record pointer, that is record pointers are 2. Right. Yes. If you are able to observe, so here the record pointer is pointing to a record, which we are searching, right. So that is what we call it as a record pointer, or simply we can call it as data pointer also, guys. So this particular point is very, very important for you. Data pointer, right. Yes. So now if I say like this, if I say this kind of a structure, if I am going to have a block, of size n, right. maximum records, maximum index records I can able to place in this block. How many? That depends upon how many number of children are there. Am I right? Yes, right. If I am going to have j children, how many number of index pointers I can able to store? Try to observe. J children are there, and each child is supposed to have a capacity of size something like some a bytes, plus how many keys are going to be there? J minus 1 keys are going to be there, right? J minus 1 keys are going to be there, and J minus 1 record pointers are going to be there, right? Record pointers, if I say RP, right? So this will be, if I try to write as BP, block pointer BP, and its size should be less than or equal to n. Am I right? Yes. So this many number of things that you have to identify, right? So if I say j block pointers plus j minus 1 keys along with their record pointers, sum should be less than or equal to size of the block, right? Hope you understood this one clearly, right? If you are unable to understood, in the few minutes you can able to understood with the help of this problem, right? Yes. Fine. So this is the structure of a BTree, right? So means this structure, the structure of the node in BTree cannot be vary. It can be in any level, right? It can be in a root node, or it can be in intermediate node, or it can be in the leaf node. Whatever the level it may be, the node structure cannot be vary, guys. Cannot be vary, right? Yes. Now, how you are thinking that this BTree is going to be efficient one? Because many data I am going to place, like I can able to place huge data, right? So if you are able to observe, you are going to have the platters, right? If you take one particular disk is going to have a collection of platters, and those are going to be placed in the form of tracks, and again each track is going to have some kind of sectors, right? This is one block, right? This block is going to be placed by this one at this particular location, and this is going to be placed by this particular location, and it is going to be placed by this particular location, like this. It is going to be completely filled, as per the storage requirement, right? And the root node is going to be supposed to fit at one particular location, yes. And when somebody wishes to read the data, first it will go for the index record, and it will try to identify which block my data contains. For example, if my data contains this particular block, then it will directly move to this particular block. That is what I said, right? Number of block access are required. We have seen the question. So this is where your BTree is going to be help in the plotters. Yes, right? Fine. So if you look into the rules of BTree, we can say the properties of BTree. So basically, you are going to have root node, right? So root node contains how many children? Root node contains minimum 2 children are there. And you can able to have maximum m children. If I am supposed to have the order of the tree is going to be m, right? And what about the internal nodes, children, right? So internal node children having minimum of m by 2, maximum it can have m children, right? If I am saying that children are m by 2, what about the keys? M by 2 minus 1, and maximum keys are m minus 1. What about the leaf level nodes? So in leaf level we are going to have keys, right? You are going to have keys, and they are going to have m by 2 minus 1 and m minus 1, minimum of m by 2 and maximum of m minus 1, right? So these are the some of the properties that you can able to understood it clearly, right? So which you heard these terminals in data structures also. Yes. For example, I will try to create one B-tree of order 3 more. Right? If I try to construct one B-tree of order 3, right? If it is B-tree of order 3, how many number of maximum keys I can able to place in a particular node? 2. What about the minimum number of keys? Minimum number of keys are going to be 1, right? Yes. For example, I would like to insert the data like 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. These are the 10 values I need to insert, right? How we are going to do? So basically, yes, we are going to have one thing, yes, one value you can able to insert it, right? Next step is you have to insert 1, 2. Now how many children are there here? This is one children, one children, one children, right? Yes, maximum number of keys 2. Now if I am going to place one more key, 1, 2 and 3, one more key, is it going to violate the rule or not? Yes. When it is going to violate the rule, you have to take out the middle value, and you have to redistribute it. What is the middle value? 2 is the middle value. I have redistributed, right? And you have to make sure that every B tree is also going to be again a binary search tree, right? Yes, 1, 2, 3. Now I need to insert the value 4. Yes, value 4 inserted. Is there any problem? No. But if I am going to insert the value 5, right? I will try to redraw once again here. 2, 1, 3, 4 and 5. If I am going to insert the value 5, again the maximum of keys are only 2, but here 3 are there, right? So you need to remove the middle one and you have to move towards the top side. So you will get 2, 4 and 1. It should be 3, it should be 5. Guys, I am trying to write this one. I am assuming that because we already know this one. 3, 5. Next value is you are trying to insert the value 6. There is no problem. Next I am trying to insert the value 7. Yes, when you are trying to insert the value 7, again it is going to violate the property, right? At this situation, what you can do, you need to take out the middle one and you are trying to move to the towards right side, top side, right? If I am trying to move this one towards top side, here also there is a violation, right? Yes. When there is a violation, again you need to make split, right? So your entire structure will look like this: 4 followed by 2. Here it will be 6. It will be 1, 3, 5 and 7, right? Yes, fine. So this is the way your order is going to be happen, right? So we done with the 7. Next we will go with 8 is going to be no problem. Next if I insert 9, there is a violation, so 8 will becomes here, right? If 8 will becomes there, your structure will look like changes: 4, 2, 6 and 8. 6 left side will be as usual and 2 left side is as usual 1 and 3. Here it will be 7 and it will be 9, right? Next I can able to place the 10 directly, right? This is the final B tree of size order 3. Okay, fine. For example, let us try to construct one more thing. It will be easy one only, right? I am going to have the data something like this: A, B, C, D, E, F, G, H, I, J, right? if the BTree of order 5, then how many maximum keys I can able to place? Yes, I can able to place a maximum of 4. Maximum of 4, right? A, B, C, D. For example, if I try to place one more value, E, then there will be a problem, right? So at the time, what you can do, you will try to split at the middle level, right? If you are trying to split at the middle level, the left side you are going to get AB, right side you are going to get DE, and at the middle you are going to get C, right? Yes. Now go with F, there is no problem, F. Then go with G, no problem. Then if I try to place H, if I place H, then you are going to get the problem, right? Meaning that this F you need to split, right? If you are going to split this F, that will be moved to the top, and this will be connected like this, right? Next, I am going to place I and then J. That's it. Let us try to perform delete operation over the bit. Guys, you know, right? So when you are going to perform any kind of delete operation, it has to follow certain structure, right? So certain structure means it has to always follow the properties of BTree, right? Yes. For example, if I try to say the earlier one, this particular structure, right? So if I try to draw this one and 10, right? Guys, for example, if I try to delete the number 10, can I delete the number 10 directly? Yes, because even if I am going to delete the data 10, there is no problem, because if I try to observe, minimum value should be, minimum key should be m by 2 minus 1. What is the value of m here? Value of m is 3. Right? So 3 by 2 minus 1. 3 by 2 minus 1 is 1 point something. So 2 minus 1 is 1. So minimum 1 key should be enough, right? So even if I am going to delete the number 10, minimum 1 key is there, so there is no problem for me, right? So once I deleted, this particular node is going to be deleted. So I have deleted 10, right? Yes. Next, now if I am asking you to delete 7, what will happen? If I delete the 7, minimum keys are going to be 0, but according to the rule it should have the minimum value 1 here. So according to the logic, you can able to get it from the left side, or you can able to get it from the right side borrow, right? Even if you go for a left side, there is no chance to get it, because it is also having the minimum 1 node, here also having the minimum 1 node, I cannot able to get. So what you can do, then you can simply merge them. So if you try to merge it, you are going to get 4, 2, 6, 1, 3, it should be 5, it should be 8 and 9. Okay, guys, I am thinking that you know the deletion as well as insertion of records in BTree. That's why I am just going like this, right? So means generally, if we are going to have the minimum keys are m by 2 minus 1, after deleting a particular node, if the number of values in the node is greater than or equal to this particular thing, then I can simply go and delete the particular node. If after deletion it is going to be less than, then what I have to do? I have to rebalance it, right? So when you are going to do this particular procedure, you can come across one particular point called underflow. Underflow means what? This condition. If the minimum number of keys are not satisfied, that kind of condition is called as underflow. What about the overflow? If the number of keys are going to be more when you are trying to insert a particular value, then we come across a situation called overflow situation, right? Hope you understood clearly, right? Yes. So this is the way you can able to perform insertion and deletion in the BTree, right? So based on this, try to solve one question. Suppose for example, there is a BTree with key size is 10 bytes. Block size is 512 bytes. Data pointer size is 8 bytes. And block pointer is 5 bytes, guys. And what they are asking is, what is the order of BTree? What is the order of BTree? Guys, you know, if you would like to find out the order of the BTree, first generally you have to know the structure of the BTree node, right? So if you look into the structure of the BTree node, it is going to have n children, and each child having connected with a block pointer, which you know, block pointer size, plus n minus 1 keys, and each key with a record pointer, and whose size should be less than or equal to 512. You know here block pointer size is 5, n into 5 plus n minus 1, key size is what? Key size is 10, record pointer size is record pointer, or we can call it as data pointer, right? Which you know, 10 plus 8, which is less than or equal to 5 and 12, right? If you try to solve it, it will be 5n plus 10n minus you will get minus 8 minus 10, so you are going to get minus 18, right? I think n is going to be redistributed, so you will get 18n, which should be less than or equal to 512, right? So which is 23n less than or equal to 530, n is less than or equal to 530 by 23, so which is approximately 23 point around something more, right? So as it is going to have 23 point around something, so n means what? Number of children, so that should be equal to 23, less than or equal to 23. So the order of the BTree is going to be definitely less than or equal to 23. Fine. Similarly, try to note down one more question. Similar kind of question only. In a BTree, suppose search key is 9 bytes, and block size is 512 bytes, record pointer is 7 bytes, block pointer is 6 bytes. Then they are asking for again to calculate order of BTree. What may be the value? You can simply substitute the values, right? Yes. So you don't know the order, so that is n into what is the block pointer? 6 plus n minus 1 into what is the key size? 9. What is the record pointer? 7, which should be less than or equal to again 512. If I say 6n plus 16n minus 16, which should be less than or equal to 512, so I think 22n less than or equal to 5. If you get 16 this side, you will get 528, right? So then n should be less than or equal to 24. You can able to calculate it, right? So these are some of the problems which might be get in the gate, right? If you look into the concept of ISAM tree, right? So earlier we have seen the multi-level indexing, right? In multi-level indexing, we can able to achieve this through many ways. One is through ISAM tree, another one is BTree, another one is b+tree, right? So far we have seen BTrees. ISAM tree means it is indexed sequential access method tree, right? It is also meant for to provide multi-level indexing, but the difference between the ISAM and BTree, b+tree is ISAM tree is a kind of a static tree, guys. Is a kind of a static tree, whereas coming to BTree and b+tree, it is going to be a dynamic tree. Dynamic tree. What the meaning of dynamic tree means? If I try to add the data to a node or to a tree, the tree is going to be growing. The tree is going to be growing from bottom to top. If I am trying to delete it, the tree is going to definitely shrinking from top to bottom according to the data what we are trying to store. According to data what we are trying to store. But whereas coming to static tree, once we created a tree, you cannot able to add you can able to add the data, but you cannot able to shrink or grow the tree. That is the meaning of static tree, meaning that once the memory is allocated, that memory is going to be fixed, guys. Fixed. For example, with this example you can able to clearly understood. If I am going to have 40 is one node, and I am going to have 20 and 33 is another node, 51 and 63 another node, 10, 15, 21, 27, 34, 37, 41, 46, 52, 56 and 64, 67. Assume that this is a kind of a tree, right? Yes. So this tree is also a binary search tree. Am I right? This is also a binary search tree, and it also a kind of B tree as of now. But if I am saying that this is a kind of indexed sequential access method tree, then what will happen now? Once this entire structure is fixed, once the memory is allocated for this particular tree cannot able to grow or cannot able to shrink. For example, if you would like to add certain nodes, something like 23, 48, 41, 42 and so on, 41 and so on, right? Now where might be the 23 is going to be inserted? 23 is less than 40, yes. 23 is between 20 and 33, so it will comes here, and 23 I need to place here. Actually I need to place here. Assume that the order of this ISAM tree is 3, what we are discussing. If the order of the ISAM tree is 3, then maximum number of children are how many? 2. Maximum number of children are 2. Then is it maximum number of keys? Maximum number of keys are 2. Then if maximum number of keys are 2, can I able to place here 23? No. So now, as it is ISAM tree, I cannot able to increase the tree. I cannot be able to grow the tree, or I can able to rebalance the tree. So for that reason, here you are going to use something like overflow chain. Something I am going to add one extra node directly, right? 23 I have added, right? Similarly, if I would like to have 48 will becomes here. Next 41. Next 42 will be coming. If 42 is coming, 42 I can able to place here. If I place here, what will happen? It is going to violate according to the maximum number of keys. So what is going to do now? We can able to add somewhere to the next level, right? These things we can call it as overflow chain nodes. Right? So when you are trying to insert new data, your actual tree is not growing. This is what you can call it as static tree. Right. So this is the way your instance is going to be performed, right? Similarly, if you would like to delete the data, if I am trying to delete the data like 42, I can directly delete, there is no problem. If I would like to delete the number 67, there is no need to worry about the rules here, because it will simply delete the data but not the memory, right? Because it is a static tree. Once we allocated a memory, I cannot able to deallocate until the entire thing is going to be completed. So simply I made here delete the data but not the complete memory. So memory is there itself, but I didn't deleted the memory. I have deleted only like something only data, right? For example, if we like to delete the 15, that is simply I will delete the 15 only. I cannot delete the complete memory. I cannot able to rebalance. But coming to BTree, we are going to simply rebalance the entire structure, right, according to the requirement. That's it, right? So this is the concept of ISAM trees, right? So the simple difference between the ISAM tree and other remaining two kind of multi-level indexing is ISM is static tree, whereas coming to BTree or b+tree is going to be a dynamic tree, right? Hope you understood clearly. Thank you.